Okay, very good morning, everyone. I am Mogana Sundaram, Assistant Professor in Water Engineering and Management at Asian Institute of Technology. I am a pleasure to host this special session on groundwater for climate adaptation. So I would like to give a brief overview of this special session. So we have four partners combinedly organizing this special session. Asian Institute of Technology, Thailand, Department of Groundwater Resources, Thailand, Konkan University, Thailand, Indian Institute of Technology, Roorkee, India. Objectives of this special session include sharing knowledge on groundwater resources management to safeguard water security in the region, and exploring the pathways and possibilities of using groundwater as one of the adaptations to climate change actions. Thirdly, identifying potential challenges and opportunities in adopting groundwater resources climate adaptation. And finally, initiating and mainstreaming the groundwater acts and policies towards sustainable and climate resilient adaptations. So the agenda of this special session goes like this. We have 5 presentations, each for 10 minutes. So after the presentations, we have the panel discussion, total for 20 minutes. So which means each panelist will be given 4 to 5 minutes time for the discussion. Finally, we have the concluding remarks. So with that, I would like to invite our first speaker for today's special session, Professor Ashim Das Gupta, Professor Emeritus from Asian Institute of Technology, to deliver the presentation.
Thank you, Dr. Mohana, for the introduction and for your invitation to participate in this special session. Well, as you see, my talk will be on role of groundwater in climate change adaptation. You have already heard over the last 2 days a lot of mention about groundwater, and you already know what is the role. So I am just here to emphasize few points. And the speakers following me will give in more detail, because I will just give an overview as the hat I am wearing now. So let me start with what is the role of groundwater. As you know, that global freshwater resources underlying in the underground aquifer systems are quite huge, are normally 2 orders of magnitude greater than what we find on the surface. Moreover, more than 1/2 of the world population is dependent on groundwater for their basic needs. It sustains lives, livelihoods, sustains ecosystems, yet groundwater are overused and undervalued. This is a very important aspect. It's very undervalued. This is where the problem is. We don't see the value of this available resources and its environment. The more important is the aquifer system, which we need to have much better knowledge before we talk about what we're going to do. So when you're talking about role of groundwater for climate adaptation, it's the role of all the hydrogeologists who have to be more proactive in helping this group of people who are talking about climate change and water interaction. because they have to put a lot of input there. So with this brief remark, I would like to flash on what is the role of groundwater in water resource systems. Of course, we know its role is to supply water. And that's what we started with historically, using pumping groundwater and keep on pumping as the demand increased. But one role we didn't pay much attention, that is the role as storage facility. And that is where the importance comes in, where groundwater can play significantly for adapting any uncertainties with the availability of water. When due to climate variability, certain period of time of the year, surface water availability is very, very low, and then we can use the groundwater. It is not that you are going to over-abstract or even mine the groundwater, but you have to find a way to use this resource. So this is the grasp of the problem. And thirdly, as a means of water quality upgrading. This is so that's the three important roles I want to point out. And very simple, how the groundwater systems work underground, as you see in this slide. Oh my goodness! I hope I can bend my neck and point this. That's the underground water system. And this slide simply tells the residence time of groundwater in the underground environment. To what extent we consider this residence time when we develop the resources. This is an important factor. This is one of the unique characteristics of groundwater. From the point of entry to the groundwater system to the point of exit, the time requirement or time taken by water to move could be hundreds, thousands, millions of years, depending on the situation there. So what is shown here is important factor. What is the important factor here is the banking analogy. A huge volume of water is in the bank. And this bank gets replenished from recharge. And also this bank provides money for using by the people for their demand meeting. So this bank analogy is very important. Income is recharge and inflow, and the expenditure is discharge and water withdrawal. And another important thing is the balance. And balance is, we always look into what is the recharge, income, inflow minus outflow. But there is a very large amount which is inherited. And that is your long-term saving, which is you create in your banking account. You keep on saving. Of course, you will use it for future time. And that is what we want to use it for, the time when you have shortage of water, when you have drought, when you have problems with the climate change impact on the weather system. So that's the simple analogy I like to mention. And this is again coming from International Association of Hydrogeology, authored by Steve Foster, who is a very close friend of mine, and we have done quite in association with DGR. Some of them are sitting here in this room. So that's the next slide. I want to talk about as important groundwater surface water relationship and groundwater pollution risk. Of course, this shows the interaction of surface water and groundwater, activities on the ground surface which contribute to the possibility of transfer of pollutants or contaminants underground and affecting the groundwater system underground. But that's, you cannot avoid that. That has been going on all the time. We have to live with it, but we have to regulate it, how this can be reduced or could be controlled. So that's important thing which is shown there. But in this groundwater and surface water, again I would like to point out, they are all originated from precipitation and from snow. That's the only similarity. When you look into other aspects, there is a lot of dissimilarity between groundwater and surface water. One of the dissimilarities is the regional flow pattern, which is quite different from...
Each sentence will be about
شلون قبل كانت هجوم قوات البحثية باليوم حملوا على حدودنا وبهاي الصورة صارت يضا مثلا عندنا كثر ناس
What is
What's
happening?
that?
Do I have to stop?
قرصتهم عقارب حياية
ما زمانی که آب اومد غافلگیرمون کرد فکر کردیم مثل اون زمانی که قبلی
Okay. I stopped, I think.
Please continue, Professor.
Okay, thank you. So there is a striking difference between the two sources with respect to water pathway, regional distribution, volume in storage, as well as flow velocities, and most importantly, the chemical behavior. So I move to the next slide to talk about impact of climate change on groundwater. So what happened? Climate change impacts in every aspects of groundwater systems. When I talk about groundwater system, all the hydrological processes interacting with the ground system, our groundwater system, and they are starting with, as you can see, looking into all the elements, groundwater surface water interaction, groundwater flow, groundwater recharge and storage, groundwater discharge, and groundwater quality. Of course, groundwater recharge has been investigated quite effectively. There are a lot of literature on that. That has received quite a lot of references in our research community as well as in our administrative system, because they always try to find out what is the groundwater recharge. Based on that, they make their decision to what extent they can be pumped.
Last 3 minutes, Professor.
Yeah. So that's the important aspect. There are indirect effects through groundwater change abstraction to changes in land use cover, and this climate change induced land use changes is referring to vegetation type changes, evolving agricultural practices, and so forth. Looking into this schematic diagram, it just shows the effect. I go back to that, and it just try to point out some schematic diagram on the effect of climate on groundwater level changes, effect of land use changes on groundwater level, and the integrated effect schematically shown here, the groundwater level in general tending to go down as an integrated consequence of various activities. Importance of groundwater for climate change adaptation. Historically, groundwater has been used as a naturally buffered system against drought, had provided excellent water supply security. Secondly, it is a system which is distributed, decentralized system, is a cost-effective solution to improve water supply, drought resilience from climate change adaptation. In principle, the presence of aquifers considerably increases water supply security in principles by providing a natural buffer. So you have to take care of this large volume of groundwater system underground. Finally, on this slide is 4 important elements which are need to be considered for climate change adaptation. Is the storage availability, supply productivity, natural quality, and pollution vulnerability. So with respect to management aspect, if you're looking into overall performance of the groundwater system on a sustainable way, so you must look into both on the supply and demand side. So that is what is the important element to look into supply management, as well as another element is to look into demand management. Now, when you talk about supply management and demand management, this has been discussed quite a lot in groundwater literature, so I am not going to elaborate on it, but it has to be integrated with enhancing aquifer recharge, and that is what is coming up as managed aquifer recharge, appropriate technology selected for the hydrogeological situation of a given location. They are often challenging to operationalize. It has simply to say that, but it has a lot of investigations needed to be carried out. So this is again coming from the Hydrogeological Society of a recent publication of 2019, which provides a strategic overview series on climate change adaptation and groundwater. This slide shows various options of having induced recharge to the groundwater system by man-made externally. It is just putting the money to the bank, how your money is coming from the surface system, excess water availability, and this shows all the alternatives available. A lot of work has been done, bit and piece here and there. We can discuss some of those during our panel discussion. So let me just go to the management current aspect and what is the management needed in future, the paradigm shift. We do a lot of models, and the current aspect of the management aspect is the managerially focused governance and management. If you want to do the whole spectrum of groundwater governance in reality, we need to broaden our domain of consideration. We need to go out of the silos of groundwater and consider the use and users and the environment together. So that's the way forward. A paradigm shift is needed in problem solving. We don't talk about only traditional risk analysis. We have to go into a quasi-scientific assessment where we bring in science, local knowledge, belief, and values together. So that's the important direction we need to take. So let me just conclude by saying a few points. Number one, of course, aquifer having a large volume of water in storage. This reality must be taken into account for the physical water security, considering groundwater in conjunction with surface water. I'm not telling that you switch over, you put off the switch of surface water and go switch on groundwater. No, you cannot do them. You just do it conjunctively. So this is, conjunctive is not 1 + 1 is 2. Conjunctive is 1 + 1 is 3 or even 4. We have to look into that mathematically. This is what we talk about. Now, seconding, climate change effects on groundwater are unique. So this again talks about the limitation, because data limitation have made it impossible to elaborate on all these aspects. So data limitation, we have to live with it. And of course, with the advancement of technology, we can use some of the satellite information also to go into this process. Finally, at this point is the managed aquifer. Research is one tool in integrated water resource management. So here we are talking about integrated water resources management. With aquifer, we can talk about integrated water management. So that include both dimension of water and their interlinkages. So ladies and gentlemen, with that few words, I would like to conclude my presentation, and final slide on this is the governance and management system. Everybody talks about governance nowadays, but are you doing the right thing? We have to sit down and see what we are doing with regard to governance and management. So this is very, very important. This should be a high priority if groundwater resources is to be secured for climate change adaptation. Thank you very much for your attention. Thank you.
Thank you very much, Professor Dasgupta, for your insightful presentation.
Sorry,
So-
I took some more time.
We will manage, Professor Dasgupta, please. Thank you very much again. Now I would like to invite our second speaker. You can go back. Dr. Tasani from Department of Groundwater Resources, Thailand.
Good morning, everyone. My name is Tasni Nertat. I'm a hydrogeologist from Bureau of Groundwater Conservation and Restoration from Department of Groundwater Resources. Today, I would like to present about the impact of climate change on groundwater and adaptation. First of all, sorry. So, I think that, for impact of climate change, actually groundwater is a vital source for use for domestic agriculture and industry. And it depends on, because of climate, the intensity of rainfall, of drought happen. Normally, groundwater is the main source to use for agriculture. So actually, the impact of climate change on groundwater can define into direct and indirect. For direct, the impact of groundwater, impact of climate change on groundwater may impact on groundwater recharge due to change in the distribution of and intensity of precipitation and evapotranspiration pattern. And also groundwater quality and groundwater storage can be influenced by the climate change as well. But actually, we cannot quantify the climate change and the seasonal and the variation in groundwater. So we have to consider both in terms of climatic and non-climatic in conjunction manner. Here is the sum of the groundwater and climate. Normally, groundwater increase seasonal in groundwater in surface water interaction, and also pattern from surface water fed irrigation recharge groundwater. And here is the conceptual of groundwater and climate that I will script. The impact of climate change on groundwater in recharge, normally influenced by the magnitude of precipitation and its intensity, seasonal and frequency and type, and soil properties or vegetation type, geology and slope, aquifer types, and groundwater use can affect the recharge rate to groundwater. A change in the amount of effective rainfall will change the recharge into groundwater, and reduction in recharge will reduce the volume of the renewable groundwater. The impact of climate change on groundwater related to discharge is related to lowering of the groundwater table, which link to baseflow and river and spring. The overpumping of groundwater to cope with the water stress is a result of the climate change. Increase of pumping lower the water table and therefore reduce the discharge to bedflow. Increased duration and frequency of drought is likely to result in greater soil moisture deficits. And during dry period, this may lead to increased evapotranspiration from groundwater. For groundwater storage, the difference of recharge and discharge is the storage. The storage is influenced by the specific aquifer property, such as storage-activity, transmissivity, and aquifer geometry, size, and type of aquifer. The deeper aquifer may influence less than the shallower aquifers. And the storage recharge due to climate change result in a reduction and renewable storage. And the reduction in groundwater is mainly due to the combined impact of overpumping and climate effects. However, we found that the contribution of the pumping could far exceed the natural recharge. For water quality, in shallow aquifer or in some area or in the coastal area, we have the quality degradation in some area. And recharge from polluted surface water body will further compromise the groundwater quality. And so, in terms of groundwater development and conservation, we need to find the measure to adaptation to climate change, which is to manage groundwater recharge, manage groundwater storage, and protection of groundwater quality, and monitoring networks, and manage demand of groundwater, and manage discharge. This is some conceptual frameworks to manage, for example, to manage the recharge area and to find a better way to use the groundwater in the wise manner to save the groundwater. And this is the problem that occur with groundwater, both in the from climate change and water security and drought. This in the left-hand side is about the problem that is decreasing in groundwater level and decreasing water flow in river water crosses and degradation of ecosystem, water quality problem, and increasing of drought damage in agriculture, increasing competition of water among sectors, and irrigation from groundwater resources. So for the answer of the measure that we have to do is to, for this decreasing groundwater levels, we found that MAR is is a good measure to help to about the groundwater decrease, and for increased water, and increased water use efficiency is a good way for water saving techniques, restoration for irrigation system, and farmer irrigation association. And change in irrigation practice is very good, especially for and when we use groundwater for agriculture. And in some crop they consume a lot of groundwater. So if we change the crop, it will help to eliminate the problem of groundwater. So this is some kinds of the problem that we will occur to groundwater. And I would like to show you just some example that Department of Groundwater Resources, we demonstrate the project site to implement the managed aquifer recharge. And we test with ASR in the area where have the high pumping of groundwater for agriculture. For example, in the Savankalok, the Sukhothai province, in the central north of Thailand. We developed the ASR site that we drill the groundwater injection well into depth. The first one is around 30 meter to 40 meter, and the second aquifer is around 77 to 85 meters. Here is some, just show you that we have test, but the efficiency of ASR is not quite good because the injection rate just only 20 to 30 cubic meter per hour. And we found that we have some clogging after we injection after 1 month. So we have to change or to adjust the water. I think the turbidity of water is a high influence in the infiltration rate of injection wells. And we
Last 3 minutes, Dr.
yeah, also we try to implement the recharge pond in other provinces, such as in the northeastern part of Thailand, where have the problem with saline water, soil water. Yeah, and so to cope with the groundwater problem, we have to know about the condition of groundwater. So we developed the groundwater monitoring network in Thailand. Right now, we monitor both in quantity and quality. We have around nearly 2,000 monitoring wells around the world, around Thailand, sorry. And we have like telemeter and automatic recorder, and also for manual measurements here. And we have the database and web base that can access from the internet from here. So, and for the change in water level, I just show you that we have when we pumped heavy groundwater for agriculture, we found that the water level declined very dramatically. From example, from 15 meter from the surface to 40 to 50. This can show you that the impact of groundwater pumping. Oh, sorry. Yeah. And this is also the monitoring network that we have. And also, we also monitor groundwater monitoring, that we have monitor point source and non-point source, and we also monitor the impact of landfills to groundwater. If you look at this map, we can show that the groundwater quality in Thailand, in northeastern part of Thailand, normally have a saline groundwater that represent in here by the pink or brown one here. You can see that, and also we monitor. This is show the example of the water quality change due to the pumping of groundwater. If you look at the map, in the green that has strip, green and red one, in the former time, the water quality is in fresh. It means TDS less than 500 milligram per liter. But right now, because we grow, the farmer, they grow corn, and because the drought, so they pump a lot of water, and so they drill deeper. Normally they drill just only 40 meters, but right now they drill deeper 50 meters. That underneath they have the layers of rock salt, so the change in groundwater quality can be detected in some area in the northeastern part of Thailand. This is an example of the change in the groundwater that occur both in the climate change or for the man-made or pumping. So the conclusion is groundwater is an important source for domestic and agriculture and industry. And so groundwater management action need to be implemented to better safeguard the vital resources. And aquifer management measures, protection and monitoring network will require financial investment if groundwater is performed critical in climate change adaptation. MAR techniques to enhance groundwater recharge are available, but Water Resource Agency must select techniques to appropriate to hydrogeologic setting and establish both water harvesting guidelines and demonstration projects. and more study need to be undertaken in the long term effect of climate change on groundwater system. That's all my presentation. Thank you very much.
Thank you very much, Dr. Tosani, for your nice presentation. Yeah, next I would like to invite Dr. Payom. You can give it. Dr. Payom from Konkan University to make a presentation.
Good morning, everyone. My talk today is related to managed aquifer recharge and groundwater for irrigation in Thailand. As Dr. Gupta and Dr. Thasni mentioned before, we have many experience in MAR and groundwater uses in Thailand because Konkan University, we have my institute, Groundwater Institute. We have some fund from the governments and also from a private sector to develop some project. Today I will share you about our experience. So you see, this is something that show about the past situation. Like we have a coping capacity to manage flood and drought, but some years the drought is very severe. So we have to sometimes buy the water from other parts, like we have to store water and drill groundwater. And after that, we try to use groundwater much and much. So the problem is declining of groundwater and reduce our resource and also reduce our coping capacity. Because climate variability and change and land use change impacts not only the flood, but it's also reduce the amount of recharge. So many projects that we use to develop to use groundwater. So some example of the groundwater project, like small well and use solar power, the big wells and the big tank, or sometimes it is the farmers self-support. They do small wells and use the diesels or some fuels. Yeah. In the future, if we try to manage the flood by using the flood amount to be as a recharge, we can make it more safe and extend or make our coping capacity is increase our coping capacity in the future. This is some example. The Coca-Cola Foundation, they give support for farmer to develop the groundwater supply tank. Now they also supply water or support farmer, not only the tank but the recharge point and parallels. Yeah. For MAR or managed aquifer recharge or MAR, it's not new, I think, because I found that in around 1,000 years ago, we have some example of MAR in the Peru, South America. They use sinkhole like recharge well or recharge pit to save water and use groundwater downstream, like here. And also now it is very popular tourist place. So from the ancient world, we changed to AR and MAR under the guideline of Dr. Peter Delon from CSIRO. Many concepts try to make MAR more safe and more environmental friendly. So for my experience, when we try to make a MAR in any location, we have to start with view investigation to see people, to see geography, geohydrology, and set up the model like database model, and calculate the water runoff, and water can be recharged, and make a plan for area-based, set up the numerical modeling, planning, target, and priority of the construction of MAR. So after that, we select the detailed study size or the construction size, and we go to construction by parallel with the monitoring system. Check the background, water level, water quality, and install the system with operation and maintenance manual. After that, we try to promote the water use efficiency and water productivity to farmer and MAR stakeholder, that we give them the MAR system. And we have a long-term MAR impact monitoring in terms of environment, economics, and social.
Last 5 minutes.
Thank you. This is some example of MAR, like recharge pit by DGR, rainwater harvesting, recharge trend in sugarcane field. That's now we call ACMAR. And so some dry well, this some dry well from by DGR, and some tourist place. They have also make a pit, like they want to show the limestone as tourist place and night market in Pak Chong, Khao Yai. They also used as a recharge pit in rainy season. And this is the example of percolation tanks we made in Prachinburi. This is some example of CSR project of TCP or Krating Dang that support us to run the project in Prachinburi River Basin. Yes, we use only the shallow system like dry wells, rooftop, recharge basin, and percolation tank. But before that, every project, after we survey the area, we make the suitability map first. The green, the yellow, it shows the suitability levels of the MAR implementation. After that, for 2 or 3 years, we build many systems and calculate the MAR water recharge amount, and also monitoring the water level that increase year by years, and also study the water quality in terms of before or background and after recharge system, and also use the model to planning the MAR system, like impact area, by the structure, and direct and indirect, and we projection to the near future for study the impact in terms of economics, that we use SROI or social of impact of investment evaluation system. This is another example in Northeast, because the Northeast we have rock salt and saline water. So we have to keep fresh water above freshwater land. So we have to concern about MAR that will impact to water salinity distribution. So after detailed study the area, we develop the models to see the water levels and salinity distribution. And we test the model and we choose what is the depth that appropriate to discharge, like shallow or deeper. The deeper one is can make some freshwater lens, but it might be impact another people beside your house. If we inject some place, the other people around will suffer from the injection. So we choose the shallow one. Yeah, this is the example. There is the example of monitoring the result of increasing water table and reduce the salinity. Yes, we also developed the MAR DSS decision support system for the local governments. Can be used this tool to develop their MAR system themselves. So we also develop the learning center and networking activity for MAR. And yeah, there are some also we have to concern to keep the fresh water in the Northeast. And I just want to promote this one because we have a challenge in MAR, because some people don't understand clear MAR. They also still make an un-MAR. Peter Delon tell me, oh, un-MAR means unmanaged. This is the important. Someone drain the wastewater to ground, or someone make the MAR in the saline soil, or some use inappropriate materials. DGR and my office try to develop the manual for good MARs. Yeah. And my last slide is convince you to talk or work more about governance system on MAR. Especially we have many people try to develop the MAR. And now we also try to make a system on manage the MAR system in Thailand. But now we are very weak in MAR governance. It means we have to convince people and try to make a system like in Australia, India, or the American system. So this is my my talk to share you in the first round today. Thank you very much.
Thank you very much, Dr. Payom, for your very useful presentation. Now I would like to invite Professor Sangam Shrestha to make a presentation.
Okay, good morning everyone. So I think I will build on what Professor Dasgupta mentioned, that groundwater can be impacted by not only climate change, but there are other several stressors like land use and land cover change, population growth, urbanization, right? So I will take one message from that. The another one is he also mentioned about paradigm shift in the groundwater management. It's about how do we improve the groundwater governance. So my presentation will be revolving around these two aspects. Actually, in AIT we have been conducting several research related to groundwater. I think many of collaborators are also in the room. So there are 3 ongoing projects, but in the interest of time, I will pick up only 2 projects related to groundwater. One is mapping groundwater resilience to climate change and human development in Asian cities, which is supported by the Asia Pacific Network for Global Change Research. And the second one is strengthening groundwater governance in rapidly urbanizing areas of Lower Mekong region. So, so one of the projects we are conducting is mapping groundwater resilience mapping groundwater resilience to climate change and human development in Asian cities. So all of these projects, some of the unique features are we are doing research. We have also capacity building component and also policy advocacy. So it's not only AIT, Academic Institute, but we are also involving several other stakeholders to design the project, right? For example, Department of Groundwater Resources from Thailand, Ministry of Natural Resources and Environment from other countries of the groundwater systems to climate change, land use and land cover change, and also population growth in 4 selected Asian cities. And you can see that we have selected Bangkok in Thailand, the Ho Chi Minh City in Vietnam, Kathmandu in Nepal, and Lahore in Pakistan. So there are 4 packages we are jointly conducting in this project. One is projection of future climate, land use and population, because that will impact the groundwater resources. And then work package 2 is related to surface and groundwater modeling. Basically, we will bring this future climate change, land use change, and also population growth to see what are the impact on the groundwater resources. And the third is assessment of the climate change, land use and land cover change, and population growth on the groundwater resources. And finally, mapping the resiliency of the groundwater systems of these 4 Asian cities to climate change. As I mentioned that it's not only AIT, we have been conducting this research, but also involving several other stakeholders. Since I have limited time, I will just present some of the findings of selected Asian cities, and I have selected Bangkok because we are in Bangkok. So these are the preliminary results of how the climate will be changing in Bangkok and its vicinity, how the land use and land cover change will be changing in future, and how the groundwater recharge and groundwater level will be changing in the future. So we found that in terms of climate change, rainfall will be increasing in the future. But there is spatial variability and also temporal variability. So it's not general that everywhere rainfall is increasing in Bangkok and its vicinity. In terms of temperature, the Bangkok and vicinity will be warmer in future. Perhaps it will reach to, the temperature will increase by 3 to 4 degrees Celsius in future. And also we have projected the land use and land cover change, and there are several scenarios we created, and one of the scenarios we created is a high urbanization scenario. So this is based on the past land use and land cover change. And we also estimated the groundwater recharge change in the future, and the far right hand side you can see that under the high urbanization scenario and climate change scenarios, groundwater recharge will be decreasing in the future. So based on this, we have tried to estimate what is the resiliency of the groundwater systems of Bangkok and its vicinity to these multiple stresses. And this is the indicator that we have used, and these indicators we developed jointly with the several stakeholders. We had several workshops and consultation, and then out of many indicators we have used this groundwater resilience indicator, which you can see here, the mathematical formula. So the resiliency of groundwater systems to climate change, and other stressor is what is the recharge, recovery to the depletion of the groundwater level in a given time. So on the right hand side, this is the selected results of groundwater resiliency of Bangkok and its vicinity to climate change and urbanization under RCP 4.5. And this dark color shows that the groundwater systems is not resilient to climate change and urbanization. And these are basically in the central and northeast part of the Bangkok. And the western part of the Bangkok is resilient to climate change and urbanization. So it means that perhaps groundwater management authority, they have to focus in the not resilient area, especially in the central and northeast part of the Bangkok. And we have many research related to the resiliency of the groundwater systems under several scenarios: low urbanization, medium urbanization, and high urbanization scenario. The another project which is also ongoing project supported by SummerNet program of Stockholm Environment Institute, and also this is one of the flagship project of the SummerNet program. And here also, as I mentioned that Professor Das Gupta mentioned, we need a paradigm shift for the groundwater management, right? So we try to see what is the current status of the groundwater governance in 4 rapidly urbanizing areas of the lower Mekong region. So we have selected the 4 rapidly urbanizing areas of lower Mekong region. One of them is the Vientiane city in Lao PDR. This is a rapidly urbanizing area. The second city we have selected is Khon Kaen, where Dr. Payam has also Groundwater Resource Institute, and this is also rapidly urbanizing area. The third one is Siem Reap in Cambodia. This is quite a popular tourist place in Cambodia. And then the fourth one is the Can Tho city in Vietnam. And as I mentioned that we have several partners, not only AIT conducting this project. So we have government agencies, we have research institutions, and also the NGOs. There are 3 work packages in this project. One is we want to see how the groundwater contributes to the sustainable development of these 4 Asian cities. The second is we want to see what is the current state of the groundwater governance. And the third one is the what is the vulnerability of the groundwater systems to climate change, land use and land cover change, and other stressors, so that the current groundwater governance can be improved to address these kind of multiple stresses. As I mentioned that we are basically working with the government agencies because they are the one who prepare the policies. They are the one who implement the policies also. So it's very essential to involve them in the project and in the research also. So we have 4 rapidly urbanizing areas, but I will just highlight the case from the Khon Kaen city, which is also rapidly urbanizing area. And Khon Kaen city is located in the northeast of Thailand, and groundwater is very important source for several beneficial uses like irrigation sector, domestic and industrial uses. Since this project is ongoing, we don't have many results, but some of the results, like you can see here, what is the impact of the multiple stresses on the groundwater resources in Khon Kaen city in Thailand. So in terms of the climate change, you can see that the rainfall will be increasing, but again there is spatial and temporal variability. Temperature will be increasing in the future, and it may increase by 4 degrees Celsius in the far future. And we also created the land use and land cover scenario, and one of the scenarios is high urbanization scenario, and based on the historical land use change. So based on that, we have used several modeling tools and techniques, and we found that the groundwater recharge will be decreasing because of these impacts, and also because of the change in the groundwater recharge, the groundwater level will be also decreasing in the future. So one of the interesting analysis we did is related to groundwater governance. So so we have developed this groundwater governance index, which consists of at least 4 dimensions of the groundwater governance. You can see on the left hand side technical aspects of the governance, legal and institutional aspect of the governance, cross-sectoral policy coordination, and operational aspect. So there are 30 indicators we have selected, and we developed the groundwater governance index. So maybe I can explain in detail in the coffee break or lunch break, but we have implemented this groundwater governance index in Khon City based on the expert consultation and also the questionnaire survey from several governmental officials and also other stakeholders. And on the right hand side you can see the results of the indicators, and the composite score of the groundwater governance index is 1.18. So the classification of the groundwater governance is, if it is the score is 0, then there is no existence of the groundwater governance, and if it is in between 2.01 to less than 3, then we classify this groundwater governance as optimal state of groundwater governance. And you can see here the score is 1.18, which is considered as acceptable state of the groundwater governance in Khon City. But if you look at this spider diagram, you can see that some of the indicators, they have very low scores, especially in the cross-sectoral policy coordination and also the operational indicators. So we can identify what are the areas of weakness of the groundwater governance, and we can recommend for the improvement. Okay. Yeah, I got the instruction that I have to wrap up. So I will skip this another project which is also funded by the Summernet program of ACI. But I want to conclude that or summarize these 2 projects. So based on the several scenario analysis, there is evidence that groundwater will be negatively impacted by the several stressors: climate change, urbanization, and also the population growth. And it's very essential to formulate the adaptation options and also evaluate them before we implement some of these adaptation options to adapt against the climate change impact on groundwater resources that Dr. Payam has highlighted some of the options like MAR. And the third is, although we have done this groundwater governance analysis in other cities, which we have not completed, but we found that the groundwater governance in Khon City of Thailand is in acceptable state, but it can be improved further. Okay, with this I would like to conclude my presentation. Thank you, Dr. Mohan.
Thank you very much, Professor Sangam Shrestha, for your useful presentation. Now our final speaker is Kashi Vishwanathan from Indian Institute of Technology, Roorkee. Please.
Okay, so I'll talk about the groundwater distribution. So we did some assessment for the base condition as well as for the future climate change period. So this is on the African river basin. Okay. So this is the overall groundwater status in Africa. So as we can see that there is a large variation in that from the northern to the southern part, and then it is estimated that 0.66 million kilometer cube this also has the range between 0.36 to 1.75 million kilometer cube. So it is very important to understand at the catchment scale or the groundwater basin scale how the groundwater is varying with respect to the different climate change scenario and different climatic variable and the land use land cover pattern changes. So in this particular study we have chosen the Omo river basin which is in Ethiopia. So as you can see that in Ethiopia there are different major river basins are there. In that you can look at that the Omo river basin is something like 100 mm per year the average recharge, so which is on a big number compared to all other basins. So that is one of the reason we chose, and then we wanted to do the estimation. So mainly we separate it into two parts, modeling the groundwater for the present historical period and also how the climate change impacts for the future groundwater thing. So why we need to do the assessment for this basin is this basin has a huge agricultural activity and several water source projects are there. So it is very important to understand how they spatially as well as the temporally varies, and it is also important for their sustainable management. And also understanding this also will give overall how the different hydrological processes that controls this groundwater distribution. But we also had different challenges. One of the challenges the data availability because of the lack of data, then but still how we can estimate better way. That is one of the challenge. And this is a detail about the study area. This is one of the second largest river basin in East Africa, next to Blue Nile River Basin, and it has a huge catchment area and also a high variation in the topographical variation. And this is a transboundary river basin and connects the different things in the downstream and upstream, both the things. And currently this has around 35 climate stations. So this is the only data it is available. And with this challenge, we found that this wet sparse model is one of the good choice for estimating the different water balance components of this whole basin. And this is a fully distributed physically based model, but the recent version estimates on the monthly scale. We have the option to estimate the different water balance components, and this is a raster based model. So this is a different data set we used for this model that varies from the DEM and then the different land use, land cover and soil and different data sets. And this is the overall methodology for developing this model, setting up this model. As I mentioned that we have to convert all this data into the raster format and then given into the things, then we can simulate on a monthly basis. The output also will be available in the raster format and then we can take it out. So this results we got from this model. This is for the overall estimate we made for the catchment outlet for the simulated runoff. Then we back estimated all the different groundwater component, the grid scale. Then this is a base flow model. So both the way we found a good agreement for the base flow and these things from this model. And this is the overall spatial distribution of the groundwater recharge for the different month. As you can see that there is a lot of variation in the summer and winter season, but rest of the season we could not see much of the variation, and we found that this variation is mainly because of the lagged effect, and it delayed the response. And then this is annual and seasonal variation of the groundwater. Here also you can see that there is a huge variation, because one of the thing is it is highly varying in terms of the topography from the upper to the downstream of the this whole basin. And this is we found recharge mostly in the upstream because of the high rainfall which receive the upstream of the basins, and then the downstream is recharge is less. So the second part is the climate change effect. Like we all know that the climate change has a great influence in even groundwater along with all other several things. So this is like very evident that it is varying under all the different scenario patterns, and this is also like studies have been conducted for the basins in Ethiopia for understanding like how the groundwater is impacted by the climate change, and the researchers found that there is a groundwater is decreasing with the different scenarios for the future climatic periods. And these are all the different models which like we chose, and here like we applied we chose the GCM, and then this was downscaled to the RCM, and finally like for the bias correction different methods were applied. I'll not go into the detail, but like we applied different bias correction method and found that the delta method was matching quite well for both temperature as well as for the precipitation. And this is the PhD work of my student. He is now performing the simulation for understanding what is the future impacts because of this climate projections. So whatever like we have done, the present one, it shows like the estimated long-term mean monthly groundwater recharge is more helpful for understanding the behavior for sustainable planning and implementation. And the overall finding reported in this study is like a suitable choice to analyze, especially selection of the wet sparse model for such a large African river basin. And this finding also suggested as like useful input for other model we can interlink and connect it to get more understanding about how the groundwater is varying. In addition, we also found like how we wanted to see how the different climate change scenarios will impact. That is under progress. So these are all the results from the bias correction. We found like the delta based bias correction is good. So this is a paper like we published for the base scenario condition, so interested can read that. So I would like to acknowledge my student and my collaborator, Professor Deepak Ray. Thank you.
Thank you very much, Dr. Kashi, for that excellent presentation. So before I go to this panel discussion, I would like to take a few questions from the audience.
Hi, hello, thank you. I listened with a lot of interest to all the presentations from Thailand, and I am particularly curious given that there's quite a lot of rainfall here. So there was a recent paper published in Science by Sham Shuddho and Richard Taylor and others that talks of something called the Bengal water machine, which is basically saying that intensive use of groundwater by farmers draws down the water table, and then the excess rainfall actually kind of works as, you know, kind of a mar, but a natural kind of a mar, because farmers are drawing down the water table and the rainfall is then recharging. So overall, even in a long term 30-year plus, there isn't much change in water levels. So are we seeing anything like that happening in any part of Southeast Asia? The very fact that intensive use of groundwater in the pre-monsoon season, pre-rainfall season, then leading to more recharge, the recharge that would have otherwise become rejected recharge. So, I mean, I know there's a strong evidence coming from the Bengal basin, but is that evidence also true in Southeast Asia? It's a general question for all of you working in the context of this region. Thank you.
Thank you for that question. Dr. Tasani, you want to answer this question? Dr. Payom?
You mentioned that the pumping that will make the groundwater decline, right? In Thailand, we have many.
fact that you are pumping and lowering the water table is creating space for more recharge to happen? That was my question. Is that mechanism happening here, given this has, you know, alluvial aquifers, also high rainfall? Not so much the drawing of the water table, that we know that, you know, if we use water it will go down, but my question is more about, does the drawing of the water table down, is it then compensated by higher recharge because of high rainfall?
Yeah, they have some area in Phitsanulok province in the Chao Phraya basin in the northern. When normally when water decline and when they have a high rainfall, the water level increase, yeah, to the some, I think it's maybe 4 or 5 meters. Yeah, but after that, if they use more groundwater, they still deeper again. Yeah, I can see that. Yeah.
Add more. Some of the in that part of Thailand, the Dr. Tasni said, maybe the flood, this flood area, maybe the impact of flood water in that area help to increase the or recharge.
Yeah, thank you for
especially
your,
in the shallow groundwater.
Thank you, Dr. Tasani and Dr. Payam for your answers. Now I would like to invite our speakers here for the panel discussion. Professor Dasgupta, Professor Sangam. So we have some specific questions to each of our speakers for this special session. Yeah, I would like to ask this specific question to Professor Dasgupta. How groundwater can be a solution for floods and droughts in any region in the world? If you could explain.
So that's the question, how groundwater can be a solution for floods and droughts in region. Yes, it can be, but as we have seen, to become a solution, it's not a straightforward solution. So we have to take a lot of things into consideration. But I leave the floor open, just go through, yes, to this question, can floodwater go on underground for future use? So I refer to a slide which is coming from cultivation area in Australia, where the CSIRO experts are scratching their head. Can we do that? Yes, it can be done. Water banking. Can we do that? Water banking is theoretically, it is possible, capturing rain water underground for future use, such as farm irrigation and town water supply. Dr. Aditi has rightly questioned whether is there any observation of level rise of groundwater table due to infiltration of rainwater or flood water. Normally when the area is flooded, of course the level rises, but we don't measure. Very simple. There is all the measurement system doesn't work at that time. But the level rises, yes. So there has to be now, in the early days, it is understood that the level rises. So the farmers were happy to get water build up for their wells when they start pumping. But now if you want to look into real MAR, then we have to really monitor them, as Dr. Poyum integrated that monitoring system in his approach in Konkan area. There are many places where they are doing this monitoring. So that's also Dr. Payam mentioned about different ASR technique. It is coming from Peter Dillon, as he indicated, from CSIRO. And they have also done some project where they have economically looked into how viable it is economically. That is very important. What benefit you get out of it, how much cost involved in implementation, operating cost as well as implementation cost, to look into that. So there are many reports available on that, and this is coming from one of the report. It shows that different infiltration basin scheme, and it indicates what are the different components of the MSR schemes. So you have to look into each component very much in detail to come up with the assessments. So that's the recent article which has been published, assessing the cost of managed aquifer recharge option to support agricultural development in different areas in Australia. Same area gets suffers from very long drought period, and suddenly after a couple of months it gets heavy rain, and which makes the system all flooded. And because of oscillation in the ocean, and this over the last 3 years, the eastern part of Australia has been suffering quite a lot on this El Nino La Nina effect. So once we see, this is the, I'm not talking about the economic evaluation, this is the results which were shown in part of that article. In fact, I looked into this article only when I got the question from our moderator a few days back. So I didn't go through everything in detail, but this clearly shows the economic aspects. When it talks about, sorry, it goes, let me bring back. Here it shows how much money has to be spent per kiloliter. That means 1,000 liter of water recharged, and what is the capital cost, medium, and what is the operating cost, what is the proportion of operating cost to capital cost. This is from the reservoir, upstream as well as on the downstream. This is from the basin, some ponds, infiltration basin. This is from the recharge weir. These are all part of MAR. It's an integrated system. In the same system, you can integrate different opportunities to do that. So that's it's a big question. It's a multi-million-dollar question to answer what really happens. But as a small scale, we should be able to do that. And it's need a concentrated effort, not by engineers, not by only hydrogeologists, but as a group of professionals coming from different disciplines to work together. Okay, so that's, I think, my last slide. I suppose, yes. So that's my answer, that it is possible.
Thank you, Professor Dasgupta, for your comprehensive answer for that question. Yeah, the second question to Sangam Shasta, what are the typical challenges and opportunities in implementing groundwater as adaptation to climate change? If you could answer in 3 minutes, that would be great.
Thank you, Dr. Mohan. Yeah, I think groundwater, plays in climate change adaptation, plays a key role. We have heard from Dr. Aditi also this morning, and Professor Dasgupta also highlighted how groundwater can be used for the climate change adaptation. But there are several challenges, and I'm speaking based on the projects I'm conducting and also the research I'm conducting. So one of the challenges is how do we know that we have groundwater resources in particular location, right? So the assessment of groundwater resources is kind of a challenge. because we have to know what is the quantity of groundwater resources available, what is the quality of groundwater resources available. So until and unless we know the groundwater availability in that particular location, perhaps we cannot use that groundwater for adaptation or whatever we say, right? So that is one of the biggest challenge, and it's not only at the local scale but also at the regional scale, right? And second challenge, I can see that okay, we promote the utilization of the groundwater resources, fine, right? So we have groundwater resources, then we promote for the adaptation, but there are several aspects. If you promote the groundwater use for the certain beneficial sectors, then there are several the consequences also. So if we don't think now and then you promote the groundwater as an adaptation option, perhaps it will bring several negative consequences. For example, you extract more groundwater, then groundwater table might decline, right? And that will have other consequences like land subsidence, groundwater quality deterioration. I think we have several examples. Even in Bangkok, there used to be very high amount of groundwater extraction, especially by the industrial sector, and there is a severe land subsidence, damage to the infrastructures like roads and buildings. So there are several sustainability aspects of the groundwater use, even we use for the climate change adaptation. The third challenge I can see is the availability of the data. So this is also based on my experience, like conducting several projects and research, because groundwater is out of mind, out of sight, right? So if you don't see these, probably you are not very keen to measure, monitor, and so on. But to understand the hydrology of the groundwater, we need those kind of data, right? So there are, of course, very limited data are available, but that's not enough. Okay, so availability of data is another challenges, and there are some solutions to the challenges. I can start like data availability. Nowadays, you can use the remotely sent satellite databases. For example, there are several satellite products like GRACE, and also if you want to see the changes in the rainfall, temperature, we have data like Aphrodite. So there are several data sets are available which we can avail for the groundwater resource assessment. I talked about another solution that Professor Dasgupta rightly mentioned, that we need a paradigm shift for the groundwater management. So we have to see what is the current state of groundwater governance, right? Particularly what are the institutions, what are the policies, regulations, also what are the capacity of the governmental agencies, whether they are at the national level or local level. So we need to build the capacity of all the individuals at all the levels, right? So there are several solutions exist, like how do we improve this groundwater governance, and there are also better practices. Even you can go to the Thailand case. The groundwater governance is very, very strong, especially in case of Bangkok. So we can learn from these kind of better case studies. So I will stop here. Thank you, Dr. Mon.
Thank you, Professor Sangam. And just this question to Dr. Payom, how this managed aquifer recharge is impacting on this groundwater resources. If you could explain in 2 minutes, it would be great.
Thank you. Because we don't have any long-term monitoring the impact of the MAR projects, our institute implement many projects, but still very short. We can see the water level is up higher, but in the long term, water quality we need to understand. We need to monitor but somehow I don't see if the project is planning in good step by step. We concern about the water quality of the water to recharge, like we make suitability maps, or we check the watershed area of the recharge structure. It is not impact in a negative impact. Like most of the project we implement in the organic farm system. It is very clean. And sometimes when we start the project in the new area, we start with the rainwater harvesting, because it's not the runoff. The water quality is good, and start with that. After the community is understand, we follow up with the other technique that low cost, like ponding or something like that, to make it possible. Because many projects in MAR is the cost is not available for farmer or community that can develop themselves. It is hard to extend the MAR system. Now we have to do it simple and low cost, and then promote the water use productivity. I'm not concerned about the impact in environment. It's mean social and economics. Sometimes people or farmer, when they get water, they go back. The labor from Bangkok go back to their lands and develop the new farm, because we give them the MAR and groundwater system. Thank you.
Yeah, thank you, Dr. Payum. Dr. Tasani, what are the groundwater acts in Thailand presently followed, and how it is likely to change in the future with respect to climate change impacts?
Groundwater Acts we established in 1977 to solve the groundwater decline and land subsidence, especially in the Bangkok and metropolitan area. And that time we implement the groundwater monitoring network to monitor the water levels, and we also, for Groundwater Acts, we declare the critical area in 7 provinces in Bangkok and metropolitan area. In this area, we have the measure that to control groundwater usage here, and we try to because the government try to change to surface water. They export water from Mekong River to and stop using groundwater for water supply, but still they still have use groundwater for industrial. It still have high pumping, but we also declare the groundwater free. If the people who deal groundwater in the critical area, they have to pay for the usage. For example, 1 cubic meter, 8.5 baht. And also we have to pay for the conservation fee, 3.5 baht. It means that if you deal groundwater and use groundwater in the critical area, you have to pay around 13 baht. And we extend the Groundwater Acts into around Thailand, but we call non-critical area. The people in that area have to pay for 3.5 baht for 1 cubic meter, and the money that go to the government and one into the research about to solve the groundwater problem. For example, we developed the groundwater modeling to estimate the sustainable yield in the area that have problem with groundwater, and to implement the MAR or try to solve the other problem like this. Because Department of Groundwater Resources, we responsible for both investigation of groundwater to use in other purpose, and also we develop the methodology to drill groundwater well, and also we have to conserve and restore the groundwater that have the contamination, and the main function is to control groundwater usage. Because when we have to manage groundwater, we would like to know how much water that stored in this area and how much water that can pump without adverse impact to the groundwater and to the environment. So our policy, for Department of Groundwater Resources, we still do a research for every discipline to solve the groundwater problem, even for climate change or for human pumping. Yeah, so that.
Yeah, thank you, Dr. Tasani. Dr. Kashi, how the groundwater resources vary spatially due to climate change impacts, if you could explain in 2 minutes.
Okay, thank you, Dr. Mugan. So it's well known that the climate change has impacts on the groundwater variation because of the climate change on the global scale or any local scale we take, there is a huge variation. It's also well accepted that the temperature is increasing and the rainfall is declining in many of the places. So it is obvious that because of the increasing in the temperature, there is more evapotranspiration, and if sufficiently the rainfall is not available, then it cannot meet the potential evapotranspiration in many of the places. So that will definitely have the influence on the groundwater recharge. So the amount of the recharge that could able to recharge may not be able to meet because of these effects. And the other hand, because of the lack of rainfall and because of this reduction in the soil moisture, we tend to pump more groundwater. That is further will add the more impacts on the overall to spatial variation of the groundwater behavior, and all these things will have a whole combined effect in terms of causing a huge variation in the spatial, especially because of the climate change effects. Yeah, thank you.
Yeah, thank you very much, Dr. Kashi, and I would like to thank all the speakers for your comprehensive presentations and very comprehensive answers to the critical questions that we have asked. I would like to close this session now. I would like to thank all the participants also. Thank you very much.